A sprinter's velocity over the course of a particular 100-meter race is approximated by the following model, where v is the velocity in meters per second and t is the time in seconds from the starting point. V of t is 0 for t between 0 and 0.2 seconds. V of t is minus 0.5 t squared plus 5t minus 0.98 for t between 0.2 and 5 seconds. And finally, v of t is 11.52 for t greater than or equal to 5 seconds. Note that the function in part A is relevant to v of t above. Now, I haven't done part A, but we can do it as we do the question. Sketch the graph of v as a function of t for the first 7 seconds of the race. So for the first 0.2 seconds, the velocity is 0. So, we have 5 units here making up 1 second. So each of these units must be 0.2 seconds. So this is 0.2 of a second. So the velocity is 0, so we just have a horizontal line. Now, for t between 0.2 and 5, we have a quadratic function of time. So we have a parabola, and because the t squared term is negative, we have an inverted parabola. Now we need to get the value of this quadratic at 0.2. So here it is. Here is v of 0.2. You see, we have to use this expression here because v of t is 0 when t is strictly less than 0.2. But v of t is equal to this quadratic for values of t greater than or equal to 0.2. Anyway, if you work out v of 0.2, if you plug 0.2 into this expression, you'll get 0. So v of 0.2 is 0, so we don't have any break or discontinuity in the graph at 0.2. Now, from the previous part, which I haven't done, this quadratic has a local maximum at 5, 11.52. That's easy to find. We just take the derivative, v prime of t, and set it equal to 0. So we solve this equation. If we do that, we get minus t plus 5 equals 0. From this we get t equals 5. So the turning point occurs at t equals 5. So to get a turning point, as you've seen before, we put the derivative equal to 0. So t equals 5, we have a turning point. And if you plug that value of 5 into this quadratic, you'll get the v value of it. So t equals 5, v is 11.52. So we go up to 11.52. So on the vertical axis, each square here is actually 1 unit. The scales are different on both axes, as you can see. So this is 10, so the next unit is 11. So 11.52 is about midway between 11 and 12, of course. So we're about here for the local max of the quadratic. Now, 0.2 is one of the roots of the quadratic, because v at 0.2 is 0. So this is the picture. Very rough sketch. It's the local max. Of course, we have symmetry about the local max. So we'll have symmetry. We can work out the other root by reflecting 0.2 through 5. And we can get the other root. But anyway, this is not the picture for values of t greater than 5. We can see that when t is greater than or equal to 5, v is 11.52. So we just have a constant function of 11.52. So we have a horizontal line coming from this point for values of t greater than or equal to 5. So we have a horizontal line from 0 to 0.2. We have a parabola from 0.2 to 5. And then for values of t greater than or equal to 5, we have a horizontal line. Because for all these values of t, v of t is a constant, namely 11.52. Find the distance travelled by the sprinter in the first 5 seconds of the race. Now, we know that speed or velocity is distance divided by time. Well, this would give us the average speed or average velocity if an object travels a distance of d in a time t. We divide the distance by the time taken. Now we can rearrange this to get the distance. Distance is velocity multiplied by time. So for example, if we look at picture over here where it's easier, it makes more sense because we're dealing with a constant speed. Suppose we want to find the distance travelled by the sprinter from 6 seconds to 7 seconds. Well, the time is 1 second and the velocity is 11.52. So the sprinter will be moving with a velocity of 11.52 meters per second for 1 second. So it's just like the area of this here. It's velocity multiplied by time, just as we have from this formula. So this makes sense. This idea of area makes sense when we're dealing with constant velocity. And that's what we're dealing with here for the straight line portion of the graph. We're dealing with constant velocity. However, it's the same is true for non-constant velocity. If we want to find the distance travelled, we get the area under the curve for any particular time interval. So if we want the distance travelled by the athlete from 1 to 3 seconds, the distance travelled over this interval of time, we just get the area under the curve. And that will involve integration. Straightforward here because we have rectangles. So here we're interested in the first 5 seconds. So we have to get the area under the velocity time graph from t equals 0 to t equals 5. This area. Of course, the area under this piece here is just 0 because the athlete wasn't moving. The athlete was stationary for the first 0.2 of a second. So what we're doing is we're integrating the velocity with respect to time. So it's v times dt. So the dependent variable is v, the independent variable is t. So this is like integrating y with respect to x to get the area under a curve. But you can see that v times dt is the same kind of form as this. Distance is velocity times time. But here, when we're calculating v times dt, we're actually getting the area of a very thin rectangle whose height is v and whose width is dt. So v times dt gives us the area of this. And then of course we're summing all of them. So we're summing this thing here, which is the distance travelled by the athlete over a tiny increment of time dt. Speed times time, or velocity times time, gives us the distance over that increment. So it kind of makes sense. So you just really need to be familiar with this formula. And then we just do a simple integration. So we're integrating from 0.2 to 5. They're the limits of integration of v, which is this expression here, v times dt. So we don't, well, I could put 0 down here, but actually we should not put 0 down here because the area is just 0 here, so we ignore this. We don't integrate from 0 to 5 because we're not, from 0 to 0.2 we don't, the velocity is not given by this. The velocity is actually 0. So just integrate from here to here. Now this is an easy function to integrate. So I've just done it here. We get 36.864. Now this is the distance, so this is going to be in meters. You see the velocity, I'll just quickly mention units here. The velocity here is in meters per second. We could write it like this. The time is in seconds. So meters per second times seconds, well that gives us meters. S to the power minus 1 by s to the power 1 gives us s to the power 0, which is 1. Find the sprinter's finishing time for the race. Well, we're dealing with a 100-meter sprint. Now that we know that the distance travelled by the sprinter is the area under the velocity time graph, what we want to do is find a time that gives us an area of 100 meters. So it's going to be some time somewhere over here. And we want the total area now under the graph to be 100 meters. So the total area now includes the region under the curve and under this parallel line, this horizontal line. We want it to be 100 meters. So we have to work out value of t will give us an area of 100 meters. Well, we know this area in here. It's 36.864 meters. So we take this number from 100. So the remaining area must be 63.136. So how do we arrive at this area? We have a rectangle here whose height we know is 11.52. I'll write it over here. 11.52 is the height. And we just need to find this distance here. So we take 63.136 and divide by 11.52, since we have the sides of a rectangle. So the distance along here is 5.48. So we want an answer to 2 decimal places. So now we can get t. We just add 5.48 onto 5. So t is 10.48. So the sprinter covers a distance of 100 meters in 10.48 seconds.